questions about anything from last time or anything? Well, today is going to be more of a philosophical lecture, more about a way of thinking in math. After you do things like Fourier analysis long enough, you kind of develop a new language for them and a new feeling. So sort of a breakthrough in this level of math class is we start thinking about functions as being points in a space. And every now and then I let slip language that kind of points in that direction. So points in a space. So back in Math 341, you probably saw an example of the continuous functions on a closed interval AB. They could be real valued or complex, but why don't we take them to be real? Continuous real valued functions on a closed interval AB. And you had a distance function, so you turn it into a metric space. That's a fancy word, just meaning there's a distance function, a metric space. With distance function, so there's going to be distance, the distance between two points, functions in other words, distance between f and g is just going to be the sup on AB of the absolute value of f minus g. So the picture would be, let's say I want to put a here and b here, and let's say I want two functions that are close together. Well, if f looks like this, and I want to think of a function g that's within epsilon, then I would take that curve plus epsilon and that curve minus epsilon. So that thing on this blue thing is f of x. And the dotted line above is f of x plus epsilon and f of x minus epsilon. Then a function g that's within epsilon of f would just be something that's in that between those two dotted lines. That's kind of a crummy picture. I don't know why. I should be able to draw it better than that. Let's see if I can erase G there. That doesn't have to be beautiful, but that, you know what I mean. It's stuck between those two things there. It might make it look better when I draw it in my office. Anyway, in that picture, the distance between F and G like I'm calling it D. The distance between F and G in that picture is less than epsilon. And so fun things when you start thinking in this context of a space and functions as being points in a space, then the Weierstrass theorem about polynomials being dense. Well, let's see. It means you can uniformly approximate a continuous function by a polynomial. That's what the Weierstrass theorem is. So uniformly approximate a continuous function by a polynomial on a closed interval AB. And in the fancy language of topology, so polynomials are dense among continuous functions, the same way the rational numbers is dense in the real numbers in terms of distance. Say Q is dense in R. And you can also think that CAB is complete. Because think what that would mean. If you have a sequence, given a Cauchy sequence, Fn that means that, let's see, given a Cauchy sequence in the distance, sense, let's see, what does that mean? That would mean the distance between Fn and Fm is less than epsilon when n and m are bigger than something. So if you have a Cauchy sequence in the distance function, in the sense of the distance function, that means that Fn is uniformly Cauchy. On AB. That was a word you learned in Math 341, and that implies it converges uniformly to a function f on AB, and we know that uniform limits of continuous functions are continuous. So we know uniform limits of continuous functions are continuous. So Fn. So that means that that uniformly Cauchy sequence is converging uniformly. So the Fn converge uniformly to F. And that means the distance from Fn to F go to 0. So I've just shown you that a uniformly Cauchy sequence converges uniformly. Let's see. So what I want to see, that's a uniformly Cauchy sequence. It converges. So the uniformly Cauchy sequence converges in the sense of distance. Check. So So you can use the same old words to mean much more fancy things. Well, I'm going to talk about Hilbert spaces today. The first Hilbert spaces were L2. Hilbert started thinking about his Hilbert spaces. Let's see, what are they? L2 on AB, little L2, I'll tell you what that is, and L2 on the real line. Okay, so Hilbert spaces have an inner product. So let's see, the inner product here would be, I'll write the inner products. First for L2 AB, the inner product of two functions is the one we've been using in our Fourier series business. If they were complex valued, you'd need a conjugate in the second variable. Little L2 is the space of square summable sequences. So they would be a sub n as n goes from 1 to infinity, such that the summation of could be the modulus if it's complex, that's little L2. And let's see, when you have this inner product, there's a norm, which is, let's see, what is it? It's f inner product with itself to the 1/2 power. And this inner product, if I take a sequence, an, and dot it with a bn, that's just going to be the summation of an bn conjugate as n goes from 1 to infinity. And the norm of a sequence is going to be summation an squared to the 1/2. Okay. And we've recently done the R version, so it's basically the same as the first line, except for integrating from a to b, you do go from minus infinity to plus infinity. So the FG would be an integral from minus infinity to infinity, and the norm would be the same thing. Same thing. Okay, well, an exciting thing that I alluded to earlier in the semester Parseval's, not Parseval, what did I say? Parseval's identity shows that Fourier series, so let's see, remember the Fourier series, f hat of n is the Fourier coefficient. Is an isometry between L2 from minus pi to pi to little L2. The length is preserved. Let's pretend 2 pi equals 1. There would be some stupid factor of pi in the thing. So we'll say modulo multiplication by some 2 pi somewhere, depending on how you define all these things. That's really interesting. It means that the Fourier coefficients are kind of like coordinates. By the way, in order to make this, I showed that this was a fact for various classes of functions, like continuous functions, piecewise C1 functions, etc., piecewise continuous functions. One thing I never did was try to extend it to Riemann integrable functions. It's because they are not complete. That space is not complete. L2 of Riemann integrable functions isn't complete. And to get this isomorphism, you would need completeness. Okay, so you need to know L2 minus pi to pi is complete. Meaning if I had a Cauchy sequence in that norm, that it would converge in L2 norm to a function in L2. It is when you use Lebesgue measurable functions that are L2 integrable, that are Lebesgue integrable. It is when L2 minus pi is the space of Lebesgue measurable functions those are the ones for which you can define Lebesgue integral. That are square integrable in the sense of Lebesgue. And so the Fourier coefficients make sense in that for that class of functions. And when you do it that way, then Bessel's inequality shows you that these things actually converge in L2. With respect to the Lebesgue integral. And so the little L2 is isomorphic to, big L2 is isomorphic to little L2 as a Hilbert space. It's hard, so that means you can't distinguish those two things. They're the same in every way. By the way, when you have an isometry, Parseval's identity shows you that, so here's an interesting fact. An isometry between Hilbert spaces easily implies that the inner products are preserved. And you actually did a homework problem sort of did that. So remember we had, what did we have? We had Parseval's identity that the L2 norm of f squared was equal to some factor of the sum of the Fourier coefficients squared. And that implies that when you take the inner product of f with g, you get the inner product in little L2. And you showed that was a consequence of Parseval's. And there was a pi somewhere in those formulas, in our formula sheet. That's nice to know. Okay, so I just wanted to say those words, because when you take a more advanced version of this course, you get to using L2 as soon as you get Bessel's inequality. And you start using L2 from that moment on. But an interesting thing that's sort of the same line of thinking is that we had the Plancherel identity. So now I want to switch to talking about the Fourier transform. And in the theory version of the Fourier transform, we take f hat of s is integral from minus infinity to infinity fx e to the minus 2 pi goes here, sx dx. And then in place of the, let's see, we have, that's the Fourier transform, and we called it capital F sometimes, and it maps the Schwartz space into the Schwartz space. In fact, it's a one-to-one onto map of the Schwartz space to the Schwartz space. And we had Plancherel identity. And this time there really is there's no 2 pi. So this means that the Fourier transform is an identity, is isometry. I guess I can take the square root here. It's an isometry in that distance of the Hilbert space norm of L2. Well, it's a classic fact that this allows you to extend the Fourier transform. We can extend f from L2R to L2R. And this is going to be an isometric isomorphism. Sometimes called an isometry. Isometric isomorphism. Fancy word for that is isometry. Okay, and I want to sketch how it's done. Okay. So step one, I'm going to give myself a function in L2, and I want to somehow figure out how in the heck I would define the Fourier transform of it. Okay, step one is to approximate f in L2 by a compactly supported thing. A sequence with compact support. Compactly supported functions. That turns out to be a snap. Let's let Fn be the characteristic function for minus n to n times f. Where that is, we've seen that thing before. The characteristic function of the closed interval is equal to 1 in the closed interval and 0 outside. So that's the characteristic function for that. And it's easy to see that those fn's go to f in L2. Because the integrals of the tail ends of f go to 0. Because when you integrate, remember we've done this, when the absolute x is bigger than n of f squared dx, that's the tail end of a convergent improper integral, and we've used the fact that that goes to 0 as n goes to infinity. So that's not a big deal. Okay, so the next step is to smooth it out. So next, approximate my compact supported thing by, I'll call it a phi n that's compactly supported and C infinity smooth in the real line. So on approx Fn by that in L2. And of course, I'm not going to do all the details here, but I'm going to give you the sort of a preview of what you'll see in a more advanced course if you ever do this kind of thing in a PDE class or someplace fancy. Okay, how would you do this? Well, I gave you a hint before. If you remember, I cooked up a compactly supported bump function. So it's the bump function trick. I need a bump function I'll call it psi. I want it to be infinitely smooth on R with support in minus 1, 1. You remember how I did that? I played around with a function that was 0 here, and on this side it was e to the minus 1 over t squared. And of course I made it 0 at 0, and those hook up and are infinitely differentiable. And then I reflected it, I translated and reflected it, and messed around and made a compactly supported bump function. So let's see, the phi I eventually got was supported between minus 1 and 1, and it was dead 0 out here, stayed 0 for a while until I got in here, and then it bumped. Stayed 0 for a while, and then it was a C infinity bump. I made it symmetric. That was nice. But the problem with that was that maybe the area underneath here wasn't 1. So I get a C infinity bump here. Call this thing psi. And then I take 1 over the, I let C equal that area under the graph. And then I take my bump. Let's see. My bump is 1 over C times phi of x, psi of x. And then the bump I'm going to use is phi sub epsilon of x, which is 1 over epsilon phi of x over epsilon. So the usual bump function trick. But this one has compact support, and that's a fantastic thing to have. Okay, and so I showed you earlier in the semester we showed a few lectures back that this thing is a smoothing operator. We showed that G goes to phi sub epsilon convolved with G is a smoothing operator. It smooths things out, and you can differentiate under the integral sign over and over again. That same argument works if the thing is L2. So I'm not going to show you that, but if you go back and look at that day and think, well, what if I knew how to do Lebesgue integration and my function was in L2? The same argument would work. In L2. We're not sweating the details here today. Okay, so that's a smoothing operator. And so, in fact, when something has compact support and you convolve with this thing, the result has compact support. So the aha is that phi sub epsilon convolved with my fn's are C infinity smooth with compact support. Okay, that's a true fact. Then the next step, I'm not going to do, there's something called Young's inequality about convolutions. So Young's inequality shows that my phi sub epsilons convolved with fn's converge in L2 to F as epsilon goes to 0. So I've got C infinity smooth compactly supported things that converges to my Fn, and my Fn converges to F. So what I've shown is here, have gotten a sequence in C0 infinity of R tending to F in L2. Okay. Let's call that F. Why don't I call it G? Let's call it G of N. Okay, so next I'm going to claim Gn. Well, I know that Gn minus f in L2 goes to 0 as n goes to infinity. I want to show that I want to use the Plancherel identity to get a Fourier transform of f. So I claim that G sub n, since it converges, is a Cauchy sequence. In L2. Oh, why would that be? You did this in Math 341. What would you do? I want to see its Cauchy, so I want to take Gm minus Gm. And show that, give me an epsilon, I want to make that small when n and m are bigger than something. And so if it converges to f, then I can do the classic thing of subtracting and adding and subtracting an f. So minus f plus f minus Gm. And triangle inequality holds in L2 norm. And so this would be less than the sum. And so because those converge to f, I can make those both less than epsilon over 2. And so sure enough, that classic trick shows you that if it converges, it's a Cauchy sequence. Okay, you did that back when you were showing that the real numbers are complete. So I know it's a Cauchy sequence. Consequently, Plancherel's identity shows that Gn hat minus Gm hat, that would be equal to Gn minus Gm L2 norm. The same inequality that shows that that's a Cauchy sequence would show that and so Gn hat is also a Cauchy sequence. Okay, maybe it doesn't feel like I need to do this, but I do. I need to know that the Gn hats converge to something. So L2 is complete. So Gn hat converges in L2 to something. Okay. And f is going to be the Fourier transform. So exciting. F is the L2 Fourier transform of f, which is merely an L2. Of little f in the L2 sense. Okay, it's the limit of the G hats. The G. Let's see. I didn't show it, but if I took two such sequences, it'd be easy to show that they had to converge to the same thing. So you can show F is uniquely determined by this. By this construction. And because I had that these GNs satisfied the Plancherel identity, this would converge to F, and this would converge to the Fourier transform of F. So from now on, I would call this thing F hat. For F and L2. Okay, so that's kind of exciting to know that you can extend the Fourier transform to L2. And then it's actually, well, it feels like it's abstractly defined, and maybe it is, but that's the natural place for it to be, because then all the limits are in L2 sense, and they all make perfectly good sense because of the Plancherel identity. Questions about that? There, I think it's worth seeing those words at least, because you're going to see them again if you continue in the subject. You might ask, why didn't we use something even nicer than the Schwartz space? C0 infinity, compactly supported C infinity things, they're actually zero outside of a compact set. Instead of the Schwartz space. Well, the main reason is because the famous Gaussian bump function, we really needed it. We really needed the fact that the Fourier transform of e to the minus pi x squared was itself. Without that, we just couldn't get rolling. And so that's why the Schwartz space was the natural space to use. And if you really go back and look at what I needed to show the facts, it was really a short list of things. That was the number one fact we needed. We needed the fact that F paired with G hat was F hat paired with G on S. That would be true on C0 infinity. What was the other thing we need? We needed the translation formula. We needed the Fourier transform of F of something plus H was equal to 2 pi I-ish, the Fourier transform of F. Those are the three biggies. And so number one there is what we wouldn't have had if we were in the compactly supported case. That's kind of a Heisenberg uncertainty thing. That you need to get out of C0 infinity if you're going to understand this thing properly. Questions about anything? Yeah.
Before, how do we know that G and half exists? And like the Fourier transforms of C0 infinity functions?
Oh, they're in S. See, I started with a function in L2, and so I got to use functions I know that have a Fourier transform. And so when those smooth things converge to compactly supported C infinity functions are in S. They're even nicer than S functions that decay rapidly at infinity. These are dead at infinity, so that's why. Oh, there was one more little topic I wanted to do about what you do with jumps. I don't think I have time to even mention it yet. But I feel like we're almost done with Fourier analysis, and now I want to spend the rest of the semester doing things related to it. And so on Wednesday, as something fun to do as a break after all this hard work, I'm going to get careful again and give you a fun, easy proof of the fundamental theorem of algebra using ideas that we've learned along the way. That is that every polynomial has a root in the complex plane. So it'll feel different than today. Today I was using words you maybe aren't terribly familiar with and using facts we don't know yet, just so you know where this subject is heading and why L2 is sort of a critical thing to have in the process. But Wednesday it'll be a different feeling because I'll do everything you need to do to see the fundamental theorem of algebra, and it won't even take me a whole 50 minutes. And it'll be easy and kind of fun, I hope. I've been thinking about this thing a long time, and for me, this is the quickest, easiest way to get the fundamental theorem of algebra. So that's an advertisement. Any last minute questions about anything? Okay.